Hello everyone, my name is Weibo Gao from the University of Science and Technology of China. Well, today I will share our work RCD Relation Map Driven Cognitive Diagnosis for Intelligent Education Systems. Here is the outline, and I will introduce our work mainly from these 5 parts. I will first give you a brief introduction. Cognitive diagnosis is a fundamental task in many scenarios, especially in intelligent education. Here is a toy example. Generally, students usually first to practice some exercises and leave their response logs. Then the goal of cognitive diagnosis is to infer their actual knowledge states on the corresponding concepts. Much attention has been drawn to this area, and in recent years, several works have been proposed. For example, in ALT or MALT, the students and exercises are represented with scalars or latent vectors, and their interactions are modeled with logistic-like functions. In DINA model, the interaction functions between student and exercise are designed based on conjunctive assumption. MF is a method from recommendation system which represents students and exercises with latent vectors, and the interaction function is inner productive. RCD learns the interaction function with neural network from data. In summary, exciting research or cognitive diagnosis can be generally categorized into two genres, which model student-exercise interaction and student-concept interaction, respectively. These methods have two major limitations. Firstly, they lack of modeling comprehensive student-exercise concept interaction relations. Generally, a cognitive diagnosis system contains students' exercises and concepts. They interact directly or indirectly. Although existing methods have made greater progress, none of them model students' exercises and concepts thoroughly, thus leaving abundant information underexploited. Secondly, they ignore educational dependencies between concepts. According to educational theory, there are multiple educational dependencies between concepts. For example, concepts with similarity can influence each other, while for concepts with prerequisites, the mastery of precursor concepts can influence their successor concepts. Most of existing methods don't consider concept relations, as they cannot effectively utilize the relational information. Thus, it is essential to consider the comprehensive interactions in the concept relations for cognitive diagnosis. However, there are two major challenges along this line. Firstly, the cognitive diagnosis system contains multiple relations. It is difficult to model comprehensive interactions. Secondly, as a general framework, RCD is expected to have the ability of extending the existing methods. It is also not easy. Before describing the details of our framework, I would like to talk about the problem definition. In our paper, we abstract the cognitive diagnosis system into the heterogeneous relation map. I will first spend a little time on introducing the relation map. The relation map presents as three local maps. Specifically, a concept dependency map with educational dependencies can be represented as a graph. In the graph, each node represents a certain concept, and the relations can be generally categorized into two types. The directed relations such as the prerequisite and the undirected relations such as similarity. The x-axis concept correlation map can be denoted as a bidirectional x-accept bipartite graph, while the nodes are x-axis and the concepts, and the relations refer to the correlations. The student access interaction data could be represented as a bidirectional student access bipartite graph, while the nodes are students and the x-axis, and the relations refer to the x-axis interactions. After introducing the above three local maps, here we define the relation map as a heterogeneous graph which naturally presents a multi-level structure. From the map level perspective, the map consists of three cross-layer local maps. From the node level perspective, each local map has a relatively independent map source, such as nodes and relations. Then we define our problem. Given students' response records and the relation map, our goal is to diagnose students' cognitive states by modeling their performance prediction process. Now let's go to our framework. The RCD model contains embedding, fusion, and diagnosis layers. In order to deal with these two challenges, we utilize the multi-level fusion layer to model the relation map, and we carefully design a general diagnosis layer for the extensibility of RCD. In the embedding layer, we utilize three trainable matrices to represent student x-axis and concept factors. In the fusion layer, we utilize multi-level fusion mechanisms to fuse multiple relations at each iteration. For the knowledge concept fusion, each concept appears in the concept dependence map and also plays an important role in the x-axis concept correlation map. Thus, we firstly fuse the concept dependence aggregation and the x-axis correlation aggregation respectively in the node level, and in the map level we update the concepts by fusing concept dependence aggregation and x-axis correlation aggregation, as well as its own embedding from the previous iteration. Similarly, for the x-axis fusion, we firstly fuse the concept correlation aggregation and the student interaction aggregation respectively in the node level. Then we update the x-axis by fusing two aggregation information as well as its own embedding. For the student fusion, we directly update the embeddings by fusing interaction aggregation. After the fusing process, we can get the vectors with relation information. Then in the diagnosis layer, we design a general diagnosis framework for the extensibility. Specifically, the diagnosis function contains the accumulation function and the scoring function. Furthermore, the scoring function contains the transform function and the utility function. By updating the specific function settings, the model can be extended to most of existing models. Additionally, to calculate the mastery levels, we need to set the x-axis factor as 0 vector in the diagnosis function. Next, I will introduce the experiments. We use two real-world datasets, assessments, and a GE. The GE dataset provides concept map, including similarity and prerequisite. Furthermore, we investigate the accessing sequences to verify the influence between concepts based on statistics. From the results, we can see that when the neighbors and the predecessors have been learned, the correctness probability is plummeted. As a key contribution of this work is the modeling of relation map. We conduct experiments to answer the following 5 research questions. To answer the research question 1 and the research question 2, we conduct experiments on the performance prediction task. From the results, we can see that RCD consistently performs the best at all datasets, and the relation map based on methods perform better than baselines. It can demonstrate that model complete and comprehensive interactions among students, accesses, and concepts is necessary. To answer the research question 3, we compare RCD with some respective heterogeneous graph modeling methods. From the results, we can see RCD achieves the better scores as a multi-level fusion modeling. These results can prove that our proposed RCD model has outstanding modeling abilities. To answer the research question 4, we conduct relation map analysis. Firstly, we measure the similarity between each pair of concepts with different relations to explore whether RCD can capture the educational relations. Then we measure the relations between accesses with different correlations to explore whether RCD can capture the correlations. After that, we visualize the student-access interaction relations to explore whether RCD can capture interactions. Relation map analysis clearly demonstrates that RCD can capture the relation between concepts, relations between accesses and logic concepts, and interactive relations between students and accesses. Finally, we evaluate the interpretability based on whether diagnostic proficiency is reasonable with given educational dependencies. To answer the research question 5, from the radar diagram, we can see concept 1, 3, and 5 get plummeted after fusing concept dependencies, and concept 4 is stable while concept 2 reduces. These observations indicate that the proficiency of similar concepts can affect each other, and the influence along prerequisite relations is only unidirectionally propagated in RCD. At last, I will make a little summary about this presentation. Cognitive diagnosis is a fundamental but challenging task to discover knowledge states of learners on specific concepts. To improve the performance of existing cognitive diagnosis methods, 2 key challenges should be solved. One is modeling the comprehensive interactions, and another is designing model as a general framework. To solve that, we proposed the RCD model, which can model the multiple relations by fusing multi-level aggregations, as well as blend the interactions and structures into current methods and improve them. Extensive experiments on real-world datasets demonstrate the effectiveness and interpretability of RCD. That is all my talk. Thanks for listening.